I'm working on a video, and it's gonna be about a game, not a speedrun, but a game. But this, for the time being, is a random video I was thinking about. I was thinking about this thing since a long time, and I just wanted to do it. Okay? So, a bunch of years ago, Vsauce released a video, and in this video, he was counting basically. So yeah, let's do it. Let's start with 0, then we have 1, then we have 2, we have 3, we have 4, we have 5, and yes, this is paint, so it's gonna be terrible, sorry. I'm using a mouse, I'm not using anything fancy. But yeah, you can continue forever, right? Yeah, this is something we learn pretty soon in school. Okay. At some point in the history of math, people kind of realized that everything didn't work at all, and it was like crazy. Like calculus didn't have a good foundation. Nothing had a good foundation. Everything was chaos. And in the middle of this chaos, some people decided, okay, we need to make it so everything in math comes from just a simple set of rules. And set, I guess, is a good word that I choose to use, because they could have started from every field of math, and they decided to start from set theory. And I'm not gonna go over the axioms, I don't even remember them all, I'm not a mathematician, to be honest. But one thing they did, and actually there are various ways to define the positive integer numbers, but one way they did it was using sets. And so they were like, okay, cool, so let's say that 0, the number 0, is an empty set. This set has nothing in it. There is a symbol for it. You might have seen it. This is the symbol for an empty set. But yeah, you can also just draw a circle and put nothing in it. And this, it has cardinality of 0, which means how many things there are in the set. So if I were to draw a set with 4 things, it could be 4 dots, 4 squares, 4 whatever. Even 4 things that are not the same, like 1 square and 4 dots. This has cardinality of 5, because it has 5 things in it. Okay. So this empty set, it has cardinality of 0, and it is also defined to be 0. This is the number 0. And then we can go forward. So if I create a set that has the number 0 in it, this has cardinality of 1 because it has 1 element. And it is also the definition of the number 1. And then I can continue. I can make a set that contains 0 and 1. And this has cardinality of 2, and it is also equal to 2. You could expand this, because again, 1, the definition of 1 is this thing here. So you could, in theory, do something like this, I guess. So this is 1, this is 0, and this in its entirety is 2, but it gets confusing. The thing is, you can continue forever. And this is a good way to generate new numbers. So again, if I have a set that has only 0 and 1, this is 2, which is the next number. So every time I have a certain amount of numbers, I can basically box them, create another set, and this set is defined to be the next number. So I can always continuously generate a new number. But then, you might want to do this. And by the rules we have established, this has to be a new number. But we already used every number, right? I mean, inside of this box, there is 0, there is 1, there is 2, there is 3, and everything else. So this seems like a paradox, but it isn't. It is consistent. There is no rule that has been broken by this. And so people decided, okay, this is something we need to accept, and this number, we need to find a name for it. And they did. They called it omega. It's not a but, it's an omega. And you can continue, and I should add, and I'll touch upon this a little bit later on, at this point, cardinality and ordinality kind of break, okay? So this set here doesn't have cardinality of omega. Don't worry too much about it, I'm gonna touch it upon later. Anyway, no one is stopping us from doing this. And this is omega plus 1. And as you might see, there's no limit. You can create omega plus 2, omega plus 3, and you get a list of omegas. Let me write a couple of them here. You can get omega plus 1000. There's no limit. It continues forever. For every natural number, you can add every natural number to an omega. And then you can box it. You can always do it. And you might see where we're going with this. This is also a new number. This is 2 times omega. And it makes sense, because we kind of do have 2 copies of omega. Because this in the top is an omega, and this is kind of another omega, right? And we can continue. We can generate 3 times omega. We can use a similar argument where we box every omega times something together with the previous numbers, and we generate omega squared. But we don't stop there. We can continue and continue, and really the end is never in sight. You can always do crazier and crazier stuff. You can reach omega to the omega to the omega to the omega to infinity, and this is not the last one. There's always another one. So this is pretty interesting. It kind of breaks your brain. But I feel like there's something more tangible that can break your brain even more. Which is a plus. So what does a plus do? If we have 2 numbers, a plus b, this is an operation, and it gives us another number. Let's call it c. So if we have 2 plus 2, this is equal to 4. There's one thing we can do with an addition, which is interesting, which is that we can repeat it. We can repeat it a lot of times. And if we do that, we get what is called a multiplication. We get a times b. And if we have something like 3 times 4, this is defined to be 3 plus 3 plus 3 plus 3. The key here is that the numbers of 3 we have used is equal to 4, which is this number. So a multiplication is a way to do a lot of additions of the same number. And that's not the last operation we learn in school, right? Because we can also have a to the b, the exponentiation. And this is a times a, you know the drill, right? Times a, and we continue times a, and we do it b times. Cool. Have you ever wondered, why do we stop here? No, really, why do we stop? There's no reason to stop after all. Like, we could create an operation, another one, and I'm gonna use a square to denote it, so a square b, and we could have it, so this is a to the a to the a b times. We could do it. There's a slight problem. So if I were to use some actual numbers, like actually let me do it this way, 5 square 3, okay, this is 5 to the 5 to the 5, okay. what is this equal to? It seems like a really big number, and it is pretty big. But if you remember some properties of exponentiation, you might remember that this can be simplified. This is actually 5 to the 5 times 5. We can multiply the exponents. So this actually becomes 5 to the 25. So this new operation, while new, it is not that new. It is basically a multiplication in disguise with one exponentiation. It doesn't really look like it is such a big step up like all the previous operations were. All the previous operations have some stuff that are unique to them. They really feel like they deserve to have a name. This operation doesn't, because again, because of this silly property, we can just simplify it to like basically a normal exponentiation. Unless we define it a little bit differently, because this property only works if the order of operation is from left to right. But if we do this, if we use parentheses, then this cannot be easily simplified, and this finally feels like a new operation. And it is a very big number. Already 5 to the 5 is something that I cannot really calculate on the on the fly. This is a very, very big number. And we do have another operation. This operation actually exists. It is called tetration. Tetration, tetra, comes from 4, which is the reason why I used a square. And we can create a fifth operation, of course. There's no reason why we should stop here. We could... And let me use a pentagon, because it makes sense, as this is the fifth operation. So A pentagon B is gonna be just A square B, and then we continue, and we do it B times, and I messed up. I know I messed up. Let me fix it. Sorry about that. Anyway, we can do this. Obviously, for the same reason as before, we do have to put some parentheses. But it works, and we can continue, and we can create a sixth operation, and a seventh. And so, yeah, we do have a list of operations. And does this remind you of anything? We have the operation number 1, which is the plus, the operation number 2, which is the multiplication, and so on. We have a list of numbers, basically. 1, 2, 3, 4. Read these numbers not as numbers, but as operations, and every operation grows faster than the previous one. And this makes sense, right? The addition doesn't really generate big numbers. The multiplication already is more efficient in generating big numbers. Like 3 times 4 is bigger than 3 plus 4. And also 3 to the 4 is bigger than 3 times 4. And believe me, 3 square 4 is also gonna be bigger. And this is a constant. Every new operation gives you bigger and bigger numbers. Or I should actually say that every new operation grows faster. And again, we have a list of infinite operations. Is there a way to generate an operation that grows even faster? An operation that we might call the omegath operation. I guess there are probably many ways to do it, but there is one canonical way that at least I found on the internet. This canonical way is interesting. It creates a table, okay? Let me put every positive integer here. And here I'm gonna put the operations. So plus, the times operation, the exponentiation, the square, the pentagon, okay? And you actually need to create this table for every number, because for example, let's say that this is the 3 table. This is what happens when I want to do 3 omega a, let's say, where a is these numbers, okay? A can be 0, can be 1, can be 2. So I'm gonna create this table just to know what the result should be. First of all, let's fill the table, okay? So this is just because this is the plus row, this is 3 plus 0, and then 3 plus 1, and so on. And then we have 3 times 0, 3 times 1, and you can see how this would extend forever, right? We have 3 to the 0, 3 to the 1, 3 to the 2, 3 square 0, 3 square 1, 3 square 2, and so on. And you create this table that is infinite in size. And then the omega operation, 3 omega a, is defined as this diagonal. So 3 omega 0, actually it shouldn't start from 0, it should start from 1. Or maybe you could do it with 0 here. It doesn't really matter, but yeah, let's say that it starts from 0. So 3 omega 0 is 3 plus 0. 3 omega 1 is 3 times 1. 3 omega 2 is equal to 3 to the 2. And then we have 3 tetrated 3, 3 pentated 3, and so on. So basically 3 omega a is actually equal to 3, and then here we need to use the 8th operation, and then a. I know this is a lot to take in, but this is where the fun part begins, because omega can be proven to grow faster than all of the previous operations, all of the infinite previous operations. And also, because omega is well defined, we can just iterate it and create the omega plus 1 operation. And it is what you might expect. A omega plus 1b is just equal to a omega a, and so on b times. And you can create omega plus 2, omega plus 3. Every operation that is an omega plus something, plus c, you can create. And after you have done it, you can make a table. You can put all of the omega plus here, so omega plus 1, omega plus 2, and so on. You can take the diagonal and create a new operation, and this is 2 times omega. And you can continue to do it. Every time you take the diagonal, you make a new step similar to what we did with the numbers before. And you can create even omega to the omega to the omega forever, and even faster growing operations than this one. This one is not the end. And this is all fine. This is fantastic. This is fun, maybe, I don't know, but it is interesting, definitely. But then, if we go back to numbers, just numbers, okay, not operations, the numbers don't stop there. Let's get back to the fact that 0, 1, 2, and so on, this set, okay, this set is a number in and on itself, which is equal to omega. But as I said before, this doesn't have cardinality omega. And this is a bit weird, but every number we have explored so far isn't exactly bigger than the previous one, when it comes to cardinality, at least. And you can kind of see it, because if I were to list every number including omega, this way, omega 0, 1, 2, and so on, I can pair them with just the normal numbers without omega. And there's a pairing, as you can see. And whenever you can do this kind of pairing between two sets, it means that they have the same cardinality. Another way to see it is that you can kind of show that all the even numbers are actually have the same cardinality as all the numbers. And you can just pair them with, you just divide by 2. So this pairing is just you divide by 2, and on the bottom you have all the natural numbers, on the top only the evens. And this works. And infinity is weird. Sometimes it can swallow you and do stuff like that, and it can swallow an infinite amount of numbers. So we can put omega here. We could also put omega plus 1 in here, and so this means that we start from 0 here, and then this would be a 1, this would be a 2, this would be a 3, this would be a 4. And yeah, so every number we have explored with the omegas don't really add to what we had before. They are just a way to denote an order. So omega comes after every other natural numbers. Omega plus 1 comes after omega. But if we don't care about the order, we just care about how much stuff we have, then they all have the same cardinality, which is called Aleph null. Is Aleph written like this? I don't remember. It is similar to an N, but it is actually an Hebrew. It comes from the Hebrew alphabet. And sadly, I don't remember if it is like an N or an inverted N. There are too many alphabets with N's in them that are slightly different. Anyway, we have Aleph null as the cardinality. But we do have Aleph 1 and Aleph 2. We do have them. And this goes on forever. Aleph 1 though, is there a way we could reach it? And spoiler, the real numbers, the cardinality of real numbers is Aleph 1. So the reals are significantly bigger than the natural numbers, because the natural numbers are they have a cardinality of Aleph null. So how could we reach Aleph 1? There is a way to kinda make sense of it. This way has to do with generating every number that we can possibly generate, doing what we did before. What we did to generate omega plus 1, 2 times omega, and we generate every possible number. Omega to the omega to the omega, blah 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 blah. Everyone. We generate every single one of them, and then we box them. This is the same thing we did before, but now we have a weird set. This is the set of really every number you can make doing whatever we did before. Okay? And this set is a number which is called omega 1. And this number finally is actually bigger than the previous one, because this set we have just created actually has cardinality Aleph 1. If you tried to put every single possible element of omega 1, so you have your 0, 1, 2, you have your omega, you have your 2 times omega, 3 times omega, omega to the omega to the omega to the omega, and so on, and more. And if you try to pair them with just the natural numbers, you can do it. You can try to do it, but at some point you will be able to generate another number that is not listed, that you can add here, the number C, and then you could also say, yeah, fine, let's just shift it over, let's put a 0 here, this is 1, this is 2, and we have everything fixed. But you can make another number, you can make D, and you can make another, it doesn't ever stop. And this is just a bigger infinity. This is just bigger. You cannot contain omega 1 in the naturals. Omega 1 is significantly bigger. Which begs the question, Can we create an omega 1 operation? I really want to know. I don't have the answer. My gut feeling says yes. My gut feeling says that there is an operation that grows faster and faster than every operation you can create the way we did before. And that operation is omega 1. But I have no idea if this operation actually exists. I know that it kind of can, because we know that the amount of operations we have created is actually omega 1. Like, is actually aleph 1. Okay? Because every possible operation we have created is associated with a number, right? And we have reached with the operations every number, omega, omega, 2 times omega, and so on. Which by definition, this set, which has everything we can think of, is omega 1, and it has cardinality aleph 1. So yes, we have enough operations, enough possible operations, okay, to reach an aleph 1 amount of operations. So the omega 1 operation might exist. There's a problem. Let's say we want to create it the same way we have created the previous one. We create our table, and we just do it. Why not? And we put our operations here, the plus, the multiplication one, the omega 1, the 2 omega, the omega to the omega to the omega to the omega, and so on. But as I showed you before, this list doesn't exist. You cannot create this list, right? You just cannot do it. Because if you could make this table, you could create this list, this column. It means that every operation could actually be paired with just one natural number, which means that the amount of operations we have here wouldn't be omega 1. It wouldn't have cardinality aleph 1, but it has. It does. So we cannot create this table, and then we cannot create our diagonal. And that means that our usual way to create more operations will not give us omega 1. So really, I don't know what to do. The one thing that I tried, which is kind of pointless, because I already knew the answer, but I kind of forgot, is the fact that we have enough operations. Okay, at least we have enough operations. I wanted to have a way to prove to myself that we could create a number of operations that has cardinality aleph 1, but that's kind of self-obvious. But I did find kind of a proof that has to do with sequences, and the fact that I proved that sequences of natural numbers can be paired with real numbers, and so they have the same cardinality. But whatever, it doesn't matter. What matters is that I don't know what the omega 1 operation would be, and I want to know. But I really don't know where to go. So if you have any idea, I don't know, tell me. You might think, okay, maybe the omega 1 operation, because we are talking about operations that are really big, is just something like, if I do a omega 1b, this gives me a very, very large number, like 1 followed by a lot of zeros. But this is actually not big. The number itself might be big, the operation is not, because even the addition, even the addition grows faster. What I mean by growing fast is that at some point, by changing the b number, I outpace another operation, and the addition outpaces this number at some point. At some point, b is gonna be so large that a plus b is gonna be greater than this number. If I add a multiplication here with the same b, and this is what it means to grow faster, if I use the same a and b, while a and b grow, the result grows faster for the multiplication than it does for the addition. And one kind of easy way to see it is just try to do, I don't know, 3 plus 4, and then try to do 3 times 4, and 3 to the 4, and every single operation you can think of. Every one of them gives you a bigger result. So this is just 7, this is 12, this I don't even want to know, to be honest. This is very big. This is like 81. Oh yeah, it is 81 actually. I think. Is it? No, it isn't. It isn't 81. Sorry. But yeah, it is pretty big. The omega operation is kind of weird because 3 omega 4 is equal to this is equal to 3 square 4. I think it might not be because I'm starting from 0 maybe, but that's just a small detail, who cares? Which means that this is 3 to the 3 to the 3 to the 3 with the parentheses, of course, which is pretty big. But in these operations you will find one that is bigger at this point. But the key is that if instead of a 4 I used a 5 or a 6 or a 7, the omega operation would get bigger and bigger, and it would outpace every other operation that I have here. So yeah, this is kind of fascinating, and the omega 1 operation I still can't wrap my head around it. And yeah, and I don't know what to say. It's been years, I don't have a solution. Sadly. So yeah, I hope you enjoyed this weird video. A new one is coming up next, I hope. And yeah, that's it.